So hi and welcome to the Code Mavens YouTube channel and the meetup group. If you are here, I'm really happy that Sourav agreed to give this half presentation or quarter presentation and mostly a pair programming style introduction to blockchain. I'm really happy that people are here who can listen and ask questions. Remember that this is going to be on YouTube, so if you don't want to be your I don't know, name or voice appear on YouTube, then ask it in the chat, and I will notice it and ask and talk about it, try to answer it. And if you are watching the YouTube video and if you enjoy this presentation and this meeting, then please also like the video and follow the channel so you will be updated later. Below the video, you will find a link to the repository that we are working on. I'll try to put everything into a GitHub repository and push out to GitHub so people who are in the channel can follow also, can pull and follow that code. And that's it. So Sourav, thank you for agreeing and to give this presentation. And it's your turn now. Please introduce yourself and let's go from there.
Yeah, thank you so much, Gabor. So I'm Sourav and I'm a core protocol engineer for CO2 Network. I have been that for the past 3.5 years maybe. And my job is basically developing blockchain protocols from scratch using Rust and a framework called Substrate. So today we'll be learning a bit about blockchain. So I'll be presenting something. I have prepared slides for that. So we'll be learning about blockchains briefly. And then we'll be moving on to creating our own blockchain from scratch using Rust, but not any framework. So it's just plain vanilla Rust and some cryptography grades. So let's get started. I'll share my screen now.
Yeah, I made you co-host, so you can share your screen. Yeah.
Can you see my screen, everyone?
Yeah. And just to know if anyone looks at me and sees that I'm looking upwards, that's because the larger screen is above my camera. So where I need to understand something and actually read the letters, and it's there. So don't worry, I'm trying to look at that.
All right, so I will minimize Zoom and let's begin.
Yeah, it's okay, good.
So this is a presentation I used when I presented for the first time in my first talk in my college. It is still relevant to us, so I'm still using this. So before starting to build our own blockchain, we should understand what a blockchain is. And to understand that, the simplest of definitions would be it's a chain of blocks. It's also the most ridiculous definition, but it's the one we're going to be working with because it's also the easiest to understand. So as anyone, like if you're a user or a developer, or anyone who's remotely concerned about blockchains, you should be primarily focused on those two things. That is, what exactly are these chains made up of, and what exactly is the data that is contained within these blocks. So when I say what data is contained, basically we care about what type of data is contained, in what format it is contained, and to what extent it is contained. And it typically varies from different blockchain to blockchain because they have different standards, but essentially it contains of two things. One is the block header and other is the transaction data. So block header contains four things, not always, but usually. One of them is hash of the previous block. So hash or a cryptographic hash is just a one-way function where you put some input and it gives you a fixed output, a random output, a random string output. And it is incredibly difficult or almost impossible to go back to the input from the output. So once you have some input and you got the output already, so you cannot guess what the input was just by looking at the output. Or you cannot mathematically or programmatically go back to the input from the output. So that's why hash functions are also called trapdoor functions. So yeah, so the current block has the hash of the previous block. That is how these blocks are chained. And then it has a timestamp. So timestamp is the timestamp when the block was added to the blockchain. And nonce is something we're gonna look at it later when we understand consensus, a particular consensus. And then Merkle root is something we're gonna look at right now. So apart from the block header, we have transaction data. So all the transactions that should be included in this block go here. And let's go to the Merkle root now. So Merkle root is basically a step-by-step hash of the transactions. So when you arrange the transactions in the way that I've arranged in the right-hand side, it forms something called a Merkle tree. And the root of that Merkle tree is called a Merkle root. So how do you you have the transactions, let's say transaction 1 to transaction 4, put them side by side, hash all the transactions. So after hashing transaction 1, you get hash 1. After hashing transaction 2, you get hash 2, so on and so forth. Then you concatenate hash 1 and hash 2, and you hash it again. So you get hash 1, 2. Do the same thing with hash 3 and 4. You get hash 3, 4. Concatenate the hashes again, then hash it again. You get the Merkle root.
Okay. Well, I have a question. The number of transactions is like always 4, or is just some
No, no, no. It can be anything. Like it depends on what blockchain you're following. So I just took 4 transactions because it was easier to demonstrate the Merkle root using 4 transactions. It
Okay.
can be 5, 6, or 10, whatever it is. I mean,
Okay.
I think ideally it should be 10. In some blockchains it is 10, but yeah, you can decide that on your own. There is no limit.
And the hashing algorithm that is used is what kind of hashing? Which hashing algorithm is one of the well-known?
For our project, we're going to use SHA-256,
Okay.
but then it varies from blockchain to blockchain and algorithm to algorithm. Some might use Blake 3, some might use something else. But for our today's project, we're going to use SHA-256.
Okay.
Yeah. So any doubts so far regarding how the Merkle root is constructed?
Yeah, more or less. Yeah, I understand.
Great. So now let's move on to some blockchain concepts. So a blockchain is decentralized. That is, it is not owned by a single entity or owned by a centralized entity. Every participant in the network owns a local copy of that blockchain, to which they contribute, and then they flood that entire contribution to the whole network, and then the whole network adds it to their own local copies. So that's how everyone has the same copy essentially at a given point of time.
Everyone has all the data?
Yeah, everyone needs to have all the data, because let's say if I add a new block to the blockchain, I have to propagate it to the network so that you guys can also add it to your chain.
Okay.
And then it's immutable because of the hashes I just mentioned. So if you change the tiniest bit in the block, then the entire block hash changes drastically. And since the blocks are linked by the hash of the previous blocks, so if the hash of one block changes, then all the hashes of the corresponding blocks that follow, they are all going to be changed. And you will be the only one with a changed blockchain. So you will be immediately kicked out of the
Yeah.
catch.
So one of the things that I'm really unclear to me is that I mean there are these nodes, I guess, right? That they are the block that on the node someone adds a new block to the chain. And if what happens if two people on two different nodes add to the same block another one? So do they have now two blocks on the same root, same parent block?
Yeah, that is actually a highly technical concept. So what you just mentioned, like if you add 2 different blocks by 2 different people and then it is propagated to the network at the same time, then what you get is called a fork. So there are different algorithms to resolve forks.
Okay.
And usually what happens is people follow the longest chain. So if the fork that you made has more blocks added to it after you added the block, then that chain is usually considered valid. And the orphan chain, that the other fork that is not considered valid, is kind of discarded, and all the transactions are rolled back. So the transaction that you added in your chain, in your block,
Okay.
and you propagated that, if it is not the longest chain, then it's kind of like the transaction get rolled back and that entire chain is discarded. And my chain gets to, like, it is the valid chain. So that is one algorithm to resolve forks. There are other algorithms. I will not go deep into that because it's like really technical, but this
Okay.
happens generally. If
Good.
a conflict, then the longest chain kind of gets validated and
Mhm.
accepted as the new chain.
Okay.
All right. So I hope immutability is clear, because data once written, it cannot be changed because of the hashes. And if you change one tiny bit in one block, then the entire blockchain becomes a different blockchain because of the hashes. So you can be easily caught and kicked out of the network because of malpractice, because only you have a different chain while everyone else has a different chain.
Right.
And then anonymity, because identities are unknown. So we don't use regular identities like email or passport or names or something to like transact on the blockchain or mine blocks on the blockchain or add blocks to the blockchain. We use something called a public key, about which we're going to look at it later.
Mhm.
So yeah. Next, it is transparent because everything that is recorded is available openly to everyone. You can always query a blockchain and see all the transactions. Like nothing is hidden to anyone. So once it is written on the blockchain, it can be viewed by anyone out there. So it's transparent. And coming back to anonymous again. So like I said, public key is used instead of regular identities like these. So public keys are just it's a long bunch of hexadecimal numbers. So it's not easily rememberable by humans, and it's not easily readable by humans also. So you can't look at two public keys and tell that this belongs to this guy and this belongs to this guy unless you have a really good memory and you can memorize all the public keys and to whom they belong to. But
Okay.
otherwise, it's kind of impossible to figure out who this belongs to. That is why it's anonymous. So yeah, now let's look a bit at public key cryptography. So it's also synonymous with asymmetric key cryptography. There is something called symmetric key cryptography, which is kind of less secure than this. So in asymmetric key cryptography, you have two separate keys, one public key and one private key. So you use the private key. The private key is basically a secret key. Like think of it as your email and password. So email you share openly with everyone, but your password you keep it secret to yourself only. So a private key is kept with you secretly, and a public key is propagated out to the world for sending money to you, or you send money to someone else using a public key, etc., etc. And because it is asymmetric, so you encrypt with one key and decrypt with other. So usually what happens during signatures is you sign a message using a private key and the other person can decrypt it using your public key.
Is it the same like what you usually use in SSH, right?
In what, sorry?
In SSH, when you're SSHing to somewhere and then
Yeah.
you're using private key and public key authentication unless you really want to type in your password every time.
Yeah. That's pretty much the same thing.
Okay.
Two keys, you use one key to encrypt and the other key to decrypt. Now it depends on you which key you use, because if you encrypt with your public key, then it has to be decrypted with your private key, which just makes no sense because nobody can decrypt that because your private key is supposedly secret to you. But if you do encrypt it with your private key, which is secret to you and you only, other people can decrypt it with your public key and they can, verify something like that. And it's more secure than symmetric key cryptography because I said in symmetric key cryptography, we use only one key for both encryption and decryption. And it is really difficult to let the other party know what exactly your key is. And it can easily be intercepted by attackers in the middle while you're sharing keys. So if the key is lost, then your entire channel is like it's compromised. And then RSA and ECC are the two most common algorithms for asymmetric key cryptography. RSA is not being used anymore, I guess, because ECC is much better than that. So to just give an example, ECC keys provide the same amount of security with almost half the size of RSA keys. So ECC keys are like much more compact and easier to handle. Plus the algorithm is modern. That's why RSA is not being used nowadays much, but ECC is really popular. So RSA uses large prime numbers and their factorization to compute the keys. So basically, you take two large prime numbers and you multiply them together. And it is understood that because if the product is also very large, because the prime numbers are very large, so it's not really easy to factorize the final product. So that is the base of RSA cryptography. And for ECC, you use elliptic curves. So you select a really large random number that's within the bound of the elliptic curve, and you multiply a generator point to that, and that gives you. Is there a chat question? No.
No, I turn this off. I have this beep whenever someone connects.
Yeah, I thought like somebody had a question or something.
No, I just I have this on. I turn this off. Sorry.
No. So like I was saying, yeah, ECC uses elliptic curves as their base, and you multiply a really large number with the generator point to get a public key, and that really large number is usually a private key. So we'll not go into the details of how these curves work, but yeah, RSA uses prime numbers and ECC uses elliptic curves. We
Okay.
will be a particular elliptic curve today. It's called SCCP to like in our project while we're building it. It is the same curve that is used by the Bitcoin blockchain. All right. Moving on, let's look at the final part of the presentation. It's some consensus mechanisms. So basically, consensus is how the blockchain arrives at a unified decision that yes, this is right and this is wrong. So the first consensus is proof of work, in which miners are the people who add blocks to the blockchain. So they solve complicated puzzles to validate transactions and create new blocks. So this requires a lot of computational power because of the nature of the puzzle. So if you remember, we saw a keyword called nonce in our block header when I was showing you the block diagram. So basically, miners iterate over all possible values of nonce, and then they try to hash the block. And if the hash of the block matches a particular difficulty that is set by the blockchain, then that block is considered valid. So let's say I start with nonce equal to 1, then I hash all the block data, and then I check the hash. If it starts with, let's say, 3 zeros, then it should be considered valid. But mine starts with 2 zeros, then that nonce is not valid. So I try with nonce 2, I do the same, I repeat the same process, hash it, check it. It doesn't, then I increment the nonce equal to 3, then I do the same thing. So it goes on and on and on until I actually find a particular nonce that satisfies the difficulty of the blockchain. Difficulty in this case is how many leading zeros the hash should start with. So if the number of leading zeros is 3, then the final hash that you get after finding the nonce, it should also start with 3 zeros. It doesn't matter what follows out of 3 zeros, but the hash should at least start with 3 zeros. So the miners try with different values of nonce until unless they get to that. And the first person who solves this is the person who gets to mine the block and get the block reward. So that is how proof of work works.
Okay.
Any doubts in this?
Yeah, it's I read about it and I still don't really understand this whole mining thing, but I wonder if that's really important for or actual implementation.
It is actually. We're going to implement a proof of work blockchain today.
Okay, good.
So which part did you not understand? I could explain it to you again.
I think we can just go on, and then if I get to that point again, then maybe that will clarify me, and then we can get back to this. Okay?
So just to explain it once more for people who had trouble understanding it the first time, proof of work is basically a consensus in which miners need to solve for a particular value of nonce that should satisfy the difficulty of the blockchain. And difficulty of the blockchain, for example, could be something like the final hash of the block would start with n number of zeros. So let's say if n equals to 2 and you choose a nonce value and the final hash of the block starts with 2 zeros, then that is considered a valid nonce and a valid block, and you get to mine that block. Mining basically means adding the block to the blockchain.
Yeah. Okay.
If you're a miner and you found the nonce first and your nonce satisfies the difficulty of the blockchain, then you get to mine the block first and get the block rewards.
Okay.
So basically, miners compete with each other to find the block, find the nonce first. Whoever finds it first, they get to mine the block and get the rewards.
Right. I think now I get it. Yeah.
Yeah. And the next consensus is proof of stake. It is a much lightweight consensus because it doesn't need miners or validators to solve complex puzzles. Validators are basically chosen based on the amount they have staked and how long they have been a network participant and how long they have staked the amount. Usually, it's about how much amount they have staked. So people argue that this is a bit centralized because of the rich get richer mentality, because whoever has the most stake usually is chosen to be the validator for the next block. So that's there. And you don't have to compete with anyone because you are chosen based on your stake. So if you're chosen as a validator, then you get to add the block to the blockchain. You don't have to like compete with the other validators to find some particular value or something and then add the block to the blockchain. So that's how it is pretty energy efficient because you just get chosen and you add the block. That's all. And the last example, the third type of consensus is proof of authority. So this is by far the most centralized consensus because only people with known authority are allowed to add blocks to the network. Like say, if you're an organization, then the board of directors or the CEO or the upper management, only they get to add the blocks because they have the authority to add the blocks. and the rest of the people are just network participants. They don't get to like participate in the governance of the chain. So that's why it is more centralized, but then it really flourishes in those cultures like corporate cultures or somewhere where you have a hierarchy. So you can think of proof of authority to be similar to proof of stake, but instead of validators or miners or block adders being chosen by the number of by the amount of the stake, they are just predefined by the authority they hold in the organization.
There is a question here. The idea is close to the question you asked before. What if two different nodes mine two blocks with the same parent? We say the node with the longer chain wins, but why? Wouldn't hacker just create extremely long chain? The proof of work proves that you used work money into creating your chain. It costs you money, so as long as a majority of players act honestly, hackers will have troubles to forge blocks that are different than what the honest players are creating. Okay, it wasn't the question, it's a clarification. Okay, thank you. Okay.
Yeah, so we can move forward.
Yeah, we can go.
All right, so this kind of ends my presentation here. So this is all I had to talk about. So this is all you should know before writing on blockchain.
Okay.
So if there are no questions, then we can directly start to the code.
Okay. So shall I share my screen now, right?
Yes. Can you please clone the repository that I just shared, the first one?
Shall I clone that repository? Okay.
Yeah.
Okay, let's just share the screen. Okay, so you were supposed to see the this one, this one you wanted, right?
Yeah.
Okay. Okay.
And you can check out to the workshop branch. I think it's called Code Maven Workshop.
Sorry. Should I check out?
Yeah.
There's a branch.
Yeah. Code-Maven-Workshop.
Maven workshop.
Code-Maven-Workshop.
Wait a second. I'll look at here. Code Maven workshop. Okay. Code Maven workshop.
Yeah.
Okay. Hopefully we are there.
Right. This is the one.
Just a second. It opens always opens in my other screen. I'll drag it here. Okay. So we have the editor open.
Yeah. So the reason why I asked you to clone is because it has some starter code that is otherwise cumbersome to write yourself.
Okay. So this is only the skeleton that we have. It is not the implementation yet.
It's not the final product. Yeah. We're going to build on top of this.
Sorry?
Yeah, let's begin then. So I'll give you a quick walkthrough of what are the files we have here. So we'll be writing code to the main file only. We're not going to create different files for the simplicity of the project. And you might want to turn off your analyzer because it's going to show a lot of red lines because the code is not complete. And so the files we have defined here is the main.rs file, which is our main file, and that is the main server file. Then there's a build.rs file that basically compiles our protobuf file. And if you go back to the proto folder,
If I go back to where, sorry?
the proto folder, the first folder.
The proto folder?
Yeah, the first folder right above src. Yeah. And you open the blockchain.proto file.
Sorry, I didn't understand.
Yeah. So this is our protobuf definition. So we have defined a service and then there are some messages. I will come back to this file later when we explain the main function. But basically, we have integrated gRPC connections to our blockchain so that our wallet can connect to our blockchain and send requests. And requests like send a transaction or get balance or get coins from the faucet. So these three things that you see on line 7, 10, and 13 from the RPC lines. So basically, those are the methods that are exposed to our client. So our client can submit a transaction to our blockchain. It can get balance from our blockchain and it can get the faucet money from our blockchain, basically.
Okay.
Yeah, and I'm using gRPC, hence the protobuf file.
Okay.
So let's go back to the main again.
Wait a second, there was some comment there. Pavel, I think that in Bitcoin's blockchain is the longest chain with the maximum aggregated POW difficulty, not simply the longest chain by the number of blocks. Okay, that was just another comment. Thank you.
Okay. So let's move on to the main function, main file. Yeah.
Yeah.
So we have a bunch of imports here. Chrono is for managing date and time. SACP is the curve that you're using for signatures and key management, public and private key. SERDE is for serializing and deserializing our transaction data mainly so that we can sign it. And SHA2 is basically the hashing algorithm, the 256. And then VecDQ is something I'm using for a transaction pool maintenance. And Arc and Mutex, we are using that for starting our blockchain server. And system time is because of timestamps again. And tonic is something we are using to handle gRPC. Otherwise, it would be almost impossible for us to develop this without tonic. And we have to write a lot of code by ourselves, which is not advisable. And then log is used for just logging info and one, logging to the console. So this pub mod blockchain is something that comes from the protobuf file. So tonic include proto gives us a module called blockchain. And the const faucet blockchain address is just a random address. I mean, it's not exactly an address, it's just a string, but since we are representing addresses as strings, so I just put it here like this as a constant, because if it is a faucet transaction, then you don't need to actually verify the sender and receiver and everything else. You just directly pass it on to the block and add it to the blockchain. So that's why I just created a separate unique address for the faucet. You can choose any address you wish, but I just chose a string to make it simple. And then line number 18 onwards to line 26, we have imports from the blockchain module that we just defined on line 12. That is the protobuf module. So I'll come back to the
36.
Sorry?
You said line 36?
No, line 18 to 26.
Okay.
So these are all the blockchain module imports that we just defined above.
Okay. These ones.
So
Yeah,
actually,
yeah.
are not defined in Rust code. This is just defined in the protobuf file, but tonic helps us create these types for us, so you can use them.
Okay.
All right, then can you go down to line 28?
28, 38?
28, yeah, just a bit above, so you can see the other code below also.
Okay.
All right. So we have a consensus trait. So basically, because we are creating a blockchain with a pluggable consensus mechanism, so we have a consensus trait that kind of like you need to implement this trait for every consensus algorithm that you write so that we can use dynamic dispatch to dynamically update the consensus whenever we're doing. Like if I want to select proof of work, I can choose proof of work. If I want to select proof of stake, I can select proof of stake. So the blockchain code doesn't change, only my consensus implementation changes based on the trait. And then we have the main function that I'll come back later after I defined everything else. So that's for the last.
Okay.
Now let's start writing code. Something that we have been waiting for so long.
Yeah. In a second, it's complaining about something.
Yeah, I mean, it will complain because a lot of things are missing.
Okay.
So I suggest for you to turn off your analyzer, disable it for the timing.
Well, okay.
I mean, unless you're not bothered by the red lines, then we can keep.
It's okay. It's okay for me. No problem.
All right. So now let's define an enum called consensus type.
Continuous type?
On line 35, let's define it.
Yeah.
You can slap a derived debug and then define the enum.
I think the best if you type in, okay, so I wanted you myself to type, but I'm not sure I understand how do you spell this, what you wanted to, continuous?
Consensus, that's the one that you see
Cons-
above. Consensus type.
Consensus type, okay. This is what you wanted?
It's still loading for me.
It takes time. Oh, I didn't know that it takes time for you to see what I'm typing.
Yes, this is what I wanted you to type.
Okay. It's just Copilot telling me. I mean, I guess it's reading your code and then it's offering me the same thing.
That is also correct, actually. I wanted you to type the same thing.
Okay.
Just add a derived debug on the above the enum.
Sorry?
Derived debug, a derived macro with debug trait implementation for the enum. Let me write it in chat.
Derive what? What should I derive here? Clone? No.
Debug.
Debug.
Yeah.
Okay. Well, maybe. Oh, okay.
Yeah, debug, not clone.
So, okay. So now that I see that there is an issue that it takes time for you to load to see what I'm typing, maybe it's really better that that we switch back to the original that you're going to type, and it's going to be faster, but it will have the same delay for all of us. What do you say?
I mean, I'm okay with typing, no worries. I can type.
Okay, so maybe it's better. So let's switch back to you. I'll leave it as it is now for myself, and then I'll stop the sharing so you can share, and then it might be easier.
Okay. One sec. Let me just check out to the workshop branch.
Okay.
Can you see my screen?
Yeah, yeah.
I'll just turn off my video.
Maybe you can enlarge the font a little bit.
Uh,
Uh,
Zoom in, you mean?
Sorry?
Do you want me to zoom in?
Yeah, zoom in. Yeah, please. Okay, that's fine. Fine.
Fine. Okay.
Thank you. And then there was a question in. Oops, I almost closed the window.
Is there a chat question?
There was.
Send sync. Okay, so send and sync are basically used to make something thread safe, because we are going to use multiple threads. So we need our consensus trait to be thread safe so that it can be passed between threads. And send and sync don't need to be defined anywhere because they are from the Rust standard library. All right, so let's begin. Are you guys able to see it in real time? Or is
Yeah,
it
you already derived. That's what I can see.
okay? That's the syntax manager. Derived debug.
I mean, if you say it as you write, then we'll see, we'll be able to understand if it happens at the same time or if we can get some delay.
All right. So I'll now define the enum, pub enum consensus type. And just for clarity, we're going to define a different type as well, a different consensus type. So let's call it proof of stake type. But we are not going to implement this today. We just have to define it so that it will be clear for you why we have different types here. And for proof of stake type, we are not going to take difficulty, rather we are going to take a min stake, and that would be a U64. So we have an enum consensus type, and we have defined two consensus types of proof of work and proof of stake. Now next, we are going to define the other data types that we are going to use. So first comes a struct called transaction. So this basically defines what our transaction is going to look like. We will essentially have a sender address, a recipient address, and an amount, and timestamp and signature. So sender receiver amount should be clear, timestamp as well. And signature is basically the signature of the sender who is sending the money to the receiver. So we're gonna call it pub from, which is a string. And it's basically a string representation of a public key. Then we're going to call pub to, which is the receiver. Again, it's going to be an address in the string representation. Then there is pub amount, which is the amount of money I'm sending. It is going to be 64. Finally, timestamp is also 64. Cool. And signature is record period. So this is our transaction type or transaction struct. So any transaction that we are going to register on the blockchain is going to be of this type, containing these information. So I'll slap a derive again because I need it to be of specific types. I need it to implement specific traits. So debug.
So I still would like to understand a little bit more here. So there is a blockchain out there functioning, right? And now what you're writing is some implementation of a node for it?
No, I am writing implementation of the blockchain itself.
The blockchain itself. So you assume that there's no blockchain, you just want to create a new blockchain, and in that blockchain, this is going to be, and for that blockchain, we'll have to have a server and clients, right?
Yes. And that is internally handled by gRPC using this definition.
The network connections are implemented this way, right? That's what you're saying.
Exactly.
Okay.
We'll learn more about that when we come to the main function, like how exactly a server is going to be implemented, how exactly our client has been implemented. So client is basically the wallet that I implemented, but I'm not going to do that today. So the second link that I sent to you, it's for the wallet. So it's already pre-built. We just use that to connect to the blockchain, and it also uses gRPC.
Yeah.
So the server part is kind of the last thing that I'm going to implement today. Before that, I'm going to write the core logic of our blockchain and define the data types.
Okay. But so the transaction has to be the same for all the clients, right? So I wouldn't be able just to implement a client for an existing blockchain without you reusing this information, right?
I don't think I understood your question. So like you want to define a client for an existing blockchain?
Yeah.
Yeah, you can do that. You don't have to create a blockchain for creating a client. Like you can create a client for Ethereum, you can create a client for Bitcoin, you can create a client for Polkadot or any other blockchain out there.
But you have to know what is the transaction format of that blockchain.
You have to know what formats they follow. Like what are the RPCs the blockchain has exposed to you that you can use in your client, what data types they use, what is the format, etc., etc. Because all the code is open source, so you can just look at the code and check out what.
Yeah. I understand. Yeah, I didn't mean that you have to find out some secrets. It's just that you have to do the same thing as they have done.
Yes.
Okay.
All right. Then I'm going to copy the same thing, the debug, clone, serialize, and deserialize, and put it there. And then I'm going to define a struct called block. So this is going to be our block structure. And our blockchain is going to be made of these blocks. So first thing that comes is the block number or the block index. Then the timestamp. Timestamp is basically the timestamp at which the block was added to the blockchain, like I mentioned earlier. And it's going to be a date time of UTC. Then we have transactions. So we'll be using the thing that we just defined here. It's going to be a vec of, well, transaction. And then we'll have a previous hash, that is the previous hash of the, that is the hash of the previous block that this block comes after. Then we'll have the hash of the current block that is going to be used for proof of work mining to check against this particular hash. Then of course the nonce. This will be calculated again and again while you're mining, just to ensure that you match the difficulty or you satisfy the difficulty of the blockchain. And then pub miner. Miner is the guy who mined this blockchain. So his address is there in the blockchain block. Any doubts here?
No, but what kind of address is there? I mean, if you have an address of someone, then there is some privacy issues, right? So it's not
No, the address is public for everyone to see. The
okay.
address basically your public key.
The public key. Okay.
So instead of storing the public key directly, because I ran into serialization and deserialization issues, so I am storing a string representation of the public key.
Okay.
So basically, a public key is something really large, like FFADCB, something like this, and it goes on. So I'm basically storing a string representation of this, like this.
Mhm.
Okay, so this is our block struct, and we're done with that. The next thing to implement is our blockchain, the struct blockchain, not the real blockchain. So the struct blockchain will have a chain that is just a web of blocks. Our chain is basically a collection of blocks. So hence the web of block. And then we are going to have a transaction pool. And this is where we're going to use the vec DQ and of transaction. And then we have the famous consensus algorithm here. And like I mentioned earlier, it's going to be a box of dynamic dispatch because we accept any consensus type that implements the trade consensus. So be it proof of work or be it proof of stake, as long as it implements the consensus trade for itself, we can accept that as the correct value for this type, for this field. Now we are done with this. So let's define our blockchain server. It's going to take a blockchain, but it's not going to be something as simple as this, because our blockchain server is actually a multi-threaded server. So on one thread, it runs the server, and on another thread, it mines the blocks. So that's why we're going to use Arc and Mutex. Arc to ensure that the references are shared safely between threads, and Mutex to ensure that only one thread modifies the chain at one time, because Mutex provides us with a lock, mutually exclusive lock. So that lock is especially helpful to ensure that only one thread modifies the blockchain at one time to prevent the data race and deadlock and everything. So yeah, this is our blockchain server. Pretty simple, just it contains the blockchain. And then let's define the proof of work struct. This struct is the type for which we're going to implement the consensus trait. It's going to have only one field. It's called difficulty. And difficulty U32 basically means if the difficulty is, let's say, 2, then that means the hash of the blocks would start with 2 zeros. So the difficulty is 4. It means the hash of the block should start with 4 zeros for it to be accepted as a valid block. So I'm taking it as U32. So anything can go here. That is under the jurisdiction of the user who is starting the blockchain. So it can be 2, 3, 4, anything that they want. So U32 for that. And then a simple implementation for proof of work, just a constructor. Mind you, this proof of work type is not the same as this proof of work variant. Those are two different things. So we'll write a function new for this. And the parameter would be, I think this is correct. Yeah, it's correct. So instead of proof of work, let's just say self to make it more generic. Yeah. So we defined a proof of work struct for which we will be implementing the consensus type later, the consensus trait later. And we also implemented a constructor for the proof of work type that gives us a proof of work object by initializing the difficulty. Now that's out of the way. Any doubts here so far? Like the types are defined so far? Or
Sorry?
anything you want to go over again?
No, no. What was the question? Sorry.
I was asking if you guys have any doubts.
Looks good so far.
Okay. So now that we are done with all the types, let's start implementing stuff, like giving meaning to the types. So the first thing we're gonna implement is just a general implementation for the consensus type enum. This is the same enum as this. And it will have a function called create consensus that takes self, sorry, ampersand self. And it returns the box consensus, which we need to use in our blockchain. So we're going to match because it's an enum. So if it is, let's say self or proof of work type of difficulty, something wrong, yeah, no body, okay. Then we are going to return box of new of proof of work. This is how we just work with boxes. So it's just plain the syntax. And difficulty. Something wrong. Okay, we have not implemented consensus for proof of work. So yeah, it will go away soon. Then let's do the same thing with self of proof of stake type. We are not going to implement that this time, but let's just have it because otherwise our enemy is not complete. I'll just put min stake, that is this. And here we can use the to do macro because we're not going to do it right now. I think it works. Cool. So what this create consensus does is it returns us a consensus, box consensus based on the type we have selected. So if we want a proof of work consensus type, then we pass on the difficulty, and then we get a corresponding box type given to us. And if we want to start with the proof of stake type, then we'll do the same thing here. Just copy and paste this. Instead of proof of work, make it proof of stake. And then instead of new difficulty, make it min stake. But we do not have a proof of stake type yet, so we are not going to implement this. Just keep it blank.
Just 1 second. Just 1 second. Sorry. So someone is asking about the to do macro. So it's just it just panics with some explanation that you're about to implement that later on. So it's just a syntax placeholder.
So when you have to return something, but you don't have a particular return for that, I generally use to do macro for when in those cases. You can do something like this also, return a empty type, but then it expects something like this. So you can't really use this. Hence, the to-do macro comes in handy. And if you want, then you can add more types also here. Like you can add a proof of authority type as well. But again, that's up to you. If you want to implement those, you can. You're free to do that. But for today's session, we're not going to implement any of these. Just the proof of work type. Okay. So it's now done. The consensus type implementation is done. Let's move on to implement block. So block implementation will have two functions. One is obviously the constructor that will give us a new block. And it has the block index, which is 64. And then you have the transactions, which is a wrap of transaction. And finally, the previous hash, which is a string. Did I misspell it? String, yeah. Cool. And it returns self, that is, it returns a block. It takes in these parameters and it returns a block to me. So we're going to construct a block. So let new block small of type block equals to self index can be written as it is, shorthand syntax. Timestamp would be UTC now, like the current timestamp, the time when this thing is executed. And then transactions again can be used as is. Previous as, same thing with previous as. That gave me everything. Okay, nice. So currently, the hash of the block is empty because we have not calculated that. We need to calculate that using the mining techniques. And the miner is also empty now because you do not know who the miner is. And the nonce is 0 again, because that's something we're going to calculate repeatedly to make sure the hash is in accordance with the difficulty of the blockchain. Now we're going to do block.hash equals to block.calculate hash. So this calculate hash method has not been defined yet. And we're going to return block. This, yeah. Now the very next function that we're going to define is calculate hash, of course. It takes a reference to self, that is, it takes a block, it's a method, and it returns a string, which is the hash of the block. So to calculate hash, we need to initialize a hasher with the SAR256 new. You can already see the syntax being suggested. Yeah. And then let's create a string to hash. We cannot directly hash the struct as it is. So we just need to create a string with the contents of the struct. So we can call it input or you can call it content, whatever says about. I just call it block content. And it's going to be, here's where we're going to use certain to serialize it into a string. What else is there? Self dot index, self dot timestamp. Basically, everything that is contained in the block, we are going to hash that. We concatenate them end to end and hash that. Self dot transactions, then self dot previous hash, and finally self dot nonce. And then we're gonna unwrap this. You should not actually force unwrap this because it's unsafe. You should check if it produces a valid result and then unwrap it or handle the result accordingly using an if let or match statement. But for simplicity, I'll just use unwrap. And then you're gonna use hasher dot update block content dot as bytes. Again, this is something that the hasher expects for us to do. And then we're going to encode that into a hex string. Oops. So now we also defined an implementation for our block. So it has a new method, a new associated function that gives you returns you a block, and then a calculate hash method that takes the content of the block and creates a hash out of it. So to use the hash to calculate the hash, we're using SHA-256. That's the hashing algorithm. So we first initialize that with the hasher, and then we create a string using Serde to string. Then we convert that string to bytes, and then we give those bytes to the hasher to actually hash it. And then finally, after hashing it, we use hex encode to encode the final hash into a readable string or a storable string, because that's what we are expecting as a return. Any doubts here?
Not from me. Thanks.
I don't see any in chats either, so I guess you can proceed. Again, this is all syntax. Like I'm not defining these functions anywhere. Like I have not defined update function anywhere, or I've not defined finalize function anywhere. It comes to me when I use this. These are all defined on this. All right, so our block implementation is done. We are almost halfway there. And then finally, big chunk of our implementation, implement consensus for proof of work. This is one of the major parts of our program. What basically this implementation is going to do is it is going to make proof of work type compatible to be used or to be returned like this, and in turn to be used in our blockchain. So currently I can't just use proof of work as a consensus because it has not implemented the consensus state yet. And it needs to implement the consensus state because I am using dynamic dispatch with box. So although I'm returning it here, you can see if I comment this, I get an error here because consensus is not implemented by proof of work yet. So if I implement this, or if I just try to write this, then you can see this error goes, because now we have an implementation for consensus for proof of work. So we can see the methods that the consensus state incorporates, these four methods. Let's just copy and paste this for simplicity. So we're going to implement these. So the first method that we're going to implement is the generate block method. Comment these because it's distracting. Yeah. So how do we generate a block when it comes to proof of work? I just explained how mining works and everything works. So how exactly do we generate a block in proof of work? So generating a block means we are finding a block that whose hash matches the difficulty parameters. So we're gonna say let mute block equals to block of new. We can see what's provided to us already. We have the index, we have the transactions, and we have the previous hash. Exactly the things that we need for this new function. We need the index, the transactions, and the previous hash, and we are getting that in this. So I can just directly pass it like this: index, transactions, and previous hash. And now I have a block. Now, what do I do with this block? I got a block, yes, but right now this block does not satisfy the difficulty. Like I do not know if it does. So I would say I would first set a target equal to 0, and I'll repeat it. How many times do I get to repeat it? I get to repeat it difficulty number of times. like I showed back then. If my difficulty is 3, then this 0 is repeated 3 times. If my difficulty is 4, it's repeated 4 times, so on and so forth. Uh, Something wrong.
And wanted you to make it U size.
Yes. I'll do one better. I'll make this U size.
Oh, okay.
Yeah. So that is done. Now we have also defined our target. Now we just need to check in a loop whether or not our block starts with this given target. So we're going to take a while loop because that's the most feasible here. And we're going to check if the block hash starts with our target. Our target is basically a string of zeros repeated a difficulty number of times. So if our difficulty is 3, then our target is 3, 3 zeros. If our difficulty is 4, then our target is 4 zeros, so on and so forth. So I'm checking if my, it's block, not black, sorry. Yeah, if the block hash starts with difficulty number of zeros, that is our target, then it's a valid block. Otherwise, I enter the loop and I increment the nonce by 1 and I calculate the hash again. So by the time I exit this loop, I expect that my block hash is actually the hash that I need. So I can just return the block. So this ends our generate block method in case of proof of work. For proof of stake, it will be substantially different. So let's not go there right now, but yeah. The reason why we have a consensus rate is because these methods are going to differ between algorithms. So for proof of work, this is different. For proof of stake, that's going to be different, so on and so forth. Let's start with the validate block now. So for validating a block in proof of work, or let's say in any consensus, it's going to be a bit generic. We're going to see that if the block's previous hash is actually equal to the previous hash, like it's storing the previous hash, and we're going to check if the block hash is actually equal to the calculated hash of the block. And then we're going to finally check if the block hash starts with the target. So those 3 things here, we're just gonna go one by one over them. The first thing, if block.previous hash equals to previous hash, not equals to previous hash, then I'm going to say that the block is not valid. So I'll return false. Then I'm going to check if the block hash is what I calculate using the calculate hash method. If it is not, then again, I return false. And finally, I'm going to check if the block hash starts with a 0 repeated difficulty number of times. So these are the 3 checks that I am checking to ensure that the block that I just received is a valid block or not. This check is necessary because the one that I calculate here has the hash as an empty string, the nonce as 0, and the minor also as this thing, an empty address. But this is changed, at least these 2 are changed when I go to generate block. So generate block updates my nonce and my hash until and unless it satisfies this difficulty. And when it satisfies the difficulty, it returns me the block. So after I'm calling this generate block function, my block has changed. At least these 2 fields in my block have changed. So because they have changed, I need to check that the current block hash equals to when I calculate the hash first. Just a fallback method, just to ensure that it all works out. All right. And then we have the start method. So the start method is where we are going to implement a separate thread that is going to start our consensus algorithm and start mining and all. So we're going to implement this a bit later. And because it returns nothing, so I can just do this and it's going to work. And for now, let's do this. Will it work or should it? Yeah, it works. Okay. We're going to implement that later. And the name function is the simplest function in this entire project. Just return the name of the consensus. That's all. Yeah. Any doubts so far? Don't worry about the start. We're gonna do that later. Very soon, in fact.
No, I think you can see, you can go ahead.
Okay. All right. So we're done with the implementation for consensus for proof of work. Now let's implement blockchain. So again, as usual, start with a constructor. And to initialize a blockchain, we are gonna start it with a consensus. First thing that we do is we need to define the Genesis block. Genesis block is the first block in the blockchain. It's called a Genesis block. So when we start a blockchain, we need to define the Genesis block. And from there, the blockchain propagates. Like new blocks get added to that. Genesis blocks, it's on this, it's consensus dot generate block. So we wrote this generate block function method to give us a block. It returns a block. So we're going to use that. And internally, it uses block of new. So we're going to pass the arguments now. So the index is, it's going to be 0 because it's Genesis block. So it starts with 0. And then we do not have any transactions yet in the Genesis block. So let's do this. We can do wake of new, or we can just do a vec macro with empty, whatever tells you about. Anything works. And finally, the previous hash is going to be 0. Because the Genesis block is the first block, so there is no previous hash as such. Hence, let's keep it 0. So that's done. Then let's add a logger. And return self. So for chain, we have our initial block ready. So it's going to be Genesis block of vec. And then for the transaction pool, it's going to be empty, vec taking new because we don't have a transaction pool yet, just while you're starting. And then the consensus, the one that we received here. So that's the constructor for the blockchain. Now we're going to define a function that is going to add a transaction to our blockchain. So it should return bool to describe the success. If the transaction was added successfully, then it's true. If it was not, then it's false. It's going to be taking a mutable self because the blockchain state is going to change once we add the transaction. So it's supposed to be mutable. And then the transaction is the transaction that we're trying to add. So like I mentioned earlier, if the transaction is from a faucet, like if it is a faucet transaction, then we are just going to skip it and return true.
What is this faucet?
Sorry?
What is this faucet mock chain address?
It's the const we have defined above. So
Okay.
basically, faucet is somewhere where you request funds from the blockchain for testing the blockchain out. So if I am requesting funds to test the blockchain out, then I don't really need to go through verification and everything because it's just a faucet request. So it should automatically pass through.
Okay.
Yeah. So I'm skipping everything that follows if the transaction is a faucet transaction. I will add a logger here. This that will say it's adding transaction to the faucet. The transaction from faucet to pool. Transaction dot from and transaction dot mount. Let's make it a bit more verbose. Say faucet address is this and amount is this. Okay, that's done. And I'm going to add this transaction to the transaction pool because even though it's a faucet transaction, it's still a valid transaction and it is supposed to be inside the pool to be mined. I have the transaction here. So, and finally, I'm returning true. Okay. So we successfully handled the faucet transaction. If it is a faucet transaction, then you log that it's a faucet transaction. Then you push the transaction to the pool and then you return true. Next, we're going to verify the transaction. If transaction dot verify. Wait, have we defined these methods before? Just a sec. Okay, no, we have not, but all right. If transaction dot verify, then just return true here. We're going to implement this later. Then if self dot check balance. So this check balance method, what it does is it checks if the sender has enough balance to send it to the receiver. If not, then return false. Sorry, this should be right. If not, transaction verify, return false. If not, then return false. Again, we're going to implement these later. So at the end, if everything is successful, like if the transaction is successfully verified and the balance checks out, like if the sender has enough balance to send to the receiver, then again, add a log, adding transaction to pool. From this to of this. Direction from and direction dot to. So we have yeah. The log is added. Now again, we're going to do the same thing that we did here. We're going to push it to the transaction pool and we're going to return true. So verify and check balance have not been defined yet. That's why we're getting this error. Let's define them. So let's first define check balance so that the error will go away. Check balance takes a reference to the blockchain. It returns the balance. Oh yeah, it also takes the address for which we are finding out the balance. So address is $str. Amount for which you are checking the balance, that is 0.64. So what this function basically does is it takes an address and it takes an amount and it checks if the address has at least this much amount present in their wallet. If it does not, then throw an error. Should not be 64, should be blue. Yeah, my bad. So let balance equals to self dot get balance of address, and if balance greater than equal to amount, then return true. Again, we get balance is not there. So let's define get balance next. Returns the balance to me 64. It takes in a reference to the self and an address for which you are fetching the balance. So let's say let mutable balance equal to 0. So how we're going to do this is we're going to query the blockchain and we're going to query every block of the blockchain. And wherever this address appears, we are going to check what is the opening and closing balance basically. And then add it to the balance that we have defined above, this mute balance, and then return that. So for block in self blockchain, so for blocks in the blockchain, and for transaction in block of transaction, because transactions is also a vector. So we're checking each transaction, and if transaction dot from address equals to the address that we have passed here, then sorry, it's not from address, it's transaction dot to address. Yeah. If transaction dot to address is equal to the address that we have passed here, that is, if the recipient is the address that we are looking the balance for, then add the amount to the balance. Extended amount. If transaction dot from address is equal to the address, that means if you have sent some money, then your balance is going to be deducted. So this is the simpler way to do this, but this might result in underflow and overflow. So it's better to use saturating sub. And then finally, the last thing, if the block miner's address is the address that we have given, or that the address is for the address which we are querying for, then add a reward for mining the block. Let's say it can be any arbitrary reward that you can set. It should be actually handled dynamically in real chains, but since it's a mock chain, let's set 20 coins as the block mining reward. And then at the end of everything, just return the balance. So to quickly go through, what we have done here is we are running a loop through the blockchain, through every block. And for every block, we are running a loop through all the transactions that are present in the block. And we are checking if the address is a receiver, then we are adding the balance to the address. And if we are If the address is a sender, then you're subtracting the balance. And at the end of everything, adding and subtracting in a loop, if the block miner's address is same as the address that we have passed here, then you're adding an additional 20 because that's the block mining reward.
Shouldn't that add also be saturating add?
There's a really low chance that it's gonna be an overflow because it's U64. But ideally, yes, it should be a saturating add. You're correct.
And what happens really if the saturating sub? So what will happen really if you have I don't know 20 in the balance and they are you're subtracting 30. Okay, so the saturating add sub will give you the sub now the sub the from the sender. So it will get you to zero, right? If you
Yes,
deduct, yeah.
but
But
ideally that should not happen because we have defined a check balance function here. So any transaction that would render your amount to go into render your balance to go into negative will not be accepted because for every transaction that you make, it is first hand checked whether or not you have enough balance in your account to send that particular amount.
okay.
So
So
unless and
there
until
is no need for the saturating sub, right? Because this is already protected here.
just a fallback, just for the sake of writing safe code.
Okay, no problem. I was one of the main. I mean, I came from Perl and Python programming, and this saturating add saturating sub, they all look nice, but it's always the question. Okay. Then what do you do? What do you do if how do you handle? I mean, there is okay. So your code didn't crash, but still you have something you have to deal with, right?
This actually is more relevant when you are adding a balance because balance adding has a chance of being overflowed. So if the balance is overflowing, then you can just say it's U64 of max.
Yeah.
I mean, we can put this here.
Okay.
Is there something wrong? Is this not?
What did it say?
It
Can you show?
said need to add it for.
Oh, because it doesn't know what is the type. Okay, it needs to know the exact integer type. So why is it not knowing what is the amount is?
Okay,
And
so
say explicitly that it's U64.
yeah, all right. So we can add that, and when it is saturated, so I think you're gonna get something like this. U64 of max is what you're gonna get if it is saturated. You are on mute. You are mute, Gabor.
Right. Yeah. I just keep clicking on mute. Sorry. So noises I might make here not disrupting. So that's fine. So I mean U64 is big, so it won't really happen probably.
Yeah.
But still, at the end, we decided that it's saturating air because it's if we have 20 left and we add 30, we don't want it to overflow, right? But we added only 20, and this subtracted from the other person 30. So we still had some. Right. So probably the bond that is checking the balance needs to also, so you probably also need to check whether it won't overflow the other one, right? And you would need to stop the transaction if it would overflow, right?
Yeah, actually, you should do that because if it overflows, then the money that you are sending that is kind of wasted. So it's
Yeah,
deducted from
exactly.
their account, but it's not deposited in their account.
Yeah. I'm just trying to think through how these things how you really use the saturating add and saturating sub, not just here in general terms, right? Because it's fine that it doesn't crash, but it still generates you invalid data or incorrect data, not invalid, right?
Yeah.
Yeah, okay. Go ahead, just no problem. Okay. We are not
That's
really
act-
building here something that it's going to be in production tomorrow.
yeah. So it's a good point. So I'm just mentioning it here that add Thatu ratings add also. All right. So we have check balance and we have get balance. Now let's add these functions. So check balance is already there, but we just need to get the arguments correct. So I'll just put them here. This is going to
Just remove
be,
the types. Yeah, yeah.
yeah, this is going to be transaction from, and this is going to be transaction dot amount. Yeah, that checks out. It doesn't need these. Yeah, right. Transaction dot amount. Something is wrong again. Expecting str.
Uh, ex- Expecting an STR and U64, and what is this from? How is it
This,
defined? Yeah, yeah. Just the ampersand was missing.
yeah. So now the only undefined thing here is verify, but that's all right because that's defined under the implementation of transactions, not for blockchain. So our blockchain implementation is essentially complete. We wrote all the functions that we need to write. Or did I miss something? Oh wait, we missed one function. My bad. We missed the mine function. So how do you mine the pending transactions? So let's call it mine pending transactions. And what it should return? It should return an option of block. That is, these transactions are mined, and now you have this block with the transaction that is just mined. So if self dot transaction pool is empty, then return none because there are no transactions to mine in the pool because it's empty. But if it is not, then let transactions equals to vec of transaction. We need to explicitly define this type because we're going to do some iterator and collect stuff. So we need to know what we're exactly collecting into. Hence the explicit definition for vec of transaction. Then we're going to write self of transaction pool. So from the pool, we are going to drain and we are going to collect. So drain is essentially how to say it? It's a decay method. Function mode self and minus public key. Yep. So this drains the transaction pool of everything and then it collects that and wraps it up in a vector. And then let's mine it. So we'll say previous block equals to self dot chain dot last. And since it returns an option, we can just use a question mark operator rather than forcibly unwrapping it. And then let's say mute block. This is going to be the current block. We need this previous block because our current block needs to have the previous block's hash. That's why we queried the current block, the previous block. And now let's create the new block. Here for readability. Previous block is just previous hash is just previous block's hash. And we're gonna clone it. Oh, wait, it's not a struct definition, it's just this. Okay. For transactions, we have the transactions already. We just drained them from the transaction pool. And for the index, we are going to do previous block of index plus one. So the index of the new block is basically the one added to the index of the previous block. And the transactions, we are returning it from the pool and adding it there. And then we are setting the minus address. So block dot minor equals to, again, we are doing it, we're converting the public key or public key into a string type. So minus of key dot serialize. And then self dot chain dot push dot block. Now we are adding the block that we just created here to the chain. And finally, you are returning some block. The block that you just added to the chain, we're returning that. So this completes our mind pending transactions method also. So what we did here first was we checked if the pool was empty. And if it was empty, then you return none. And next, if it was not empty, then you fetch the transactions that are in the pool. And then you check if the previous block exists. And if it exists, then you fetch the previous block. And then you create the current block with the data that you fetch from the previous block and the transactions that you drain from the pool. And then you add the minus address. And finally, after doing that, you push the block. No doubts here, I hope. And so let's proceed.
It looks good for so far, what I understand.
Okay, then we can proceed. We are at the last stages of our blockchain. We only need to define two more traits, two more implementations. We need to implement two more implementation for two more types. So let's implement transaction, the big boy. For transaction, there is a constructor as usual. It's going to return self. And it's going to take from, which is an ampersand address, ampersand string, and it's going to take a two, which is the receiver's address in string. And then it's going to take the amount, because the other things we can calculate, but these things you need as the user input. So that's there, and then return self. So from, it's from dot to string, and two is same, two dot to string. Amount can be used as is because it's already in the right format. And then timestamp, we're gonna do some really weird stuff here. So we're gonna do system time of now, then duration of since, Unix epoch. So Unix epoch is something we are importing above. This system time and Unix epoch all come from here. STD time. And then dot expect some random message, let's say invalid time or something. And finally, as seconds. That gives us our timestamp in the desired format. And signature, since there is none so far, so signature is going to be just an empty vector. And there we have a new transaction object returned using the new function. Right. So once this is done, the next thing to implement is the message to sign. So we'll call it get signing message and self. And the message is going to be a string. So when signing anything, you first hash them. Like if you have a raw text message, you first hash the message and then you sign the hash of that message. You don't sign the message directly. So like earlier, we're going to define a hasher that is SR256 of new. And then we're gonna update the hasher before, and we're gonna use SR2 string. So self dot from, self dot to, self dot amount, self dot timestamp. I don't need this. Yeah. Dot unwrap dot as bytes. Or did I do it in the wrong place? Yeah, I did it in the wrong place. Okay, now it's correct. Yeah. So finally return the hasher, but finally whatever you finalize, return that. How do you return that? You return that as a vec. Guess I messed up the return types here. Signature is a vec, so that have it as a vec of UAD. Yeah, now we're gonna signing this vec of UAD. So what we did here was we generated a message for us to sign. And how did we do that? We created a string message using JSON2 string, and we converted that to bytes, and we use those bytes in the hasher, hash them, and finally we are returning the hashed bytes as vec. So basically the resultant vec that we are returning here is the final thing that we are going to sign. We're going to put our signature on. So that's there. And finally we write the function verify that has been showing us as back then. Verify would return a bool, that is if the verification is successful or not. So to verify, we're going to check if the transaction is a faucet transaction. If it is, then just ignore it. It's true always. We don't need to further verify anything. Else, if it is not, then create an SCCP object. So SCCP 256K1 is the elliptic curve that we are going to use for generating key pair and signing. So we are using this particular elliptic curve to generate our key pair, and we are using an algorithm called ECDSA that is based on this curve that is responsible for signing. So ECDSA is a signing algorithm that is based on the SCCP curve. So we created an instance of this SCCP type, SCCP new, and then we're gonna verify whether or not the public key that was sent to us is valid or not. So we are going to match it, hex decode, self dot from. So okay, of bytes. Like if we could successfully decode that, then it's cool. Okay, of bytes and return the bytes. If there is some error, then return the error. Not exactly return, just use the warn macro. Error decoding public key and use the error that you just got there. Return false, of course. So yeah, now that's done. But semicolon, yeah, good to go. And then next, we are going to check the validity of the public key from the public key bytes that we just received. So public key equals to match. There's just a lot of validation here because these are really sensitive affairs. So you're sending money. So if it doesn't go to the right place, or if it is not from the right place, then it can go and land up anywhere. You are going to lose real money. So all these checks are to ensure that you don't lose your money. Public bytes. Okay, so if it's okay, then return the key to me. If it is an error, again, log a warning. So yeah, return false. Yeah. Public key validation is done here. So at least after this point, we are sure that the public key that is sending this transaction is actually a valid public key. Now let's proceed to signing the transaction, or at least verifying the sign of the transaction. Signature equals to CTSA. This is the algorithm that I talked about.
Sorry?
Sorry?
Yeah, did you ask something?
Oh, no, no, no. I'm just saying that this HDCA is the algorithm that I talked about, the signature algorithm here, and signing. So this is the algorithm that is used for signatures.
Okay.
It's from compact self dot signature. So what I am doing here is basically converting the signature from whatever type I had defined to the actual signature type that is defined by ECDCA for further processing. And then I'm gonna create the message again because it's a good practice to create the signing message on your end also while verifying the signature. And then let share. GitHub Copilot is kind of really smart. Like it suggests almost the exact correct thing almost all the time. Then I'm gonna return the verification result of the signature. I'll take the message. I think it will be confused which message to take. So let's call this MSG. And let's also give them the signature and the public key. And finally, if it is okay, then cool. Lastly, return false. If none of these work, then it's false by default. So the transaction verification is not a success. It's false by default. All right, the transaction implementation is also done. So is there any doubts? Are there any doubts?
Not from me.
I'll just go through the verify function again. So you are verifying if it's a faucet transaction, then you're skipping it. Then you are decoding the public key bytes and you are checking if the public key is valid or not. And then finally, you are checking the signature. So you are creating a signature type, and then you are also getting the message. And then
Mhm.
you are constructing a message type that is defined by SCCP using your string message that you just constructed. And once you are done with constructing the signature and the message, you are finally verifying that against the public key. So you verify the sign, which you sign something using a private key, but you verify that using a public key. So if this verification is successful, it means you are the one who signed it.
Okay.
All right. And finally, the last thing that you need to implement is our blockchain server. So we're going to create a blockchain server type. I think we created this earlier. We're not creating a type. Yeah, we have the type already, blockchain server, that takes a blockchain, that is architects of a blockchain, and blockchain is this. So a function new. So constructor is also done. Finally, the last thing that is left to implement is the service, this particular blockchain service, like the RPC service for our blockchain server. So our blockchain server needs to expose RPC endpoints for our client to connect. And the RPC service is defined in this protobuf file. So you need to implement this particular thing, this blockchain service. It's not a trait yet, it's just a service according to the protobuf file. But since we are using Tonic to compile, we already have a trait with the same name that has these same methods. A method called submit transaction, method called get balance, and method called request faucet. So we're just going to implement that trait for our server. It's going to be an async trait by Tonic. So the required macro. Function transaction. There's not add transaction. I'll just open this side by side. And I'll zoom out just a bit. So the methods we have on us are submit transaction, get balance, and request faucet. The first method is going to be submit transaction. And it's going to take a self as the first parameter. And then there's going to be request, which is of type request and auto transaction. So these are the types that we have implemented or we have imported basically from above. So we have a request, response, and status from Tonic, and we have proto transaction from blockchain, which is the module we have just defined above. Submit transaction, and it returns a result of response transaction a response and status. Let transaction equals to request dot into inner. So this into inner is again something that is given to us by tonic. I have not defined this anywhere. So this into inner basically gives us the message. So if I don't put into inner, if you can see the type. The type is of request and then the generic type T. So in our case, the generic type T is transaction. So it has three things, two of which I don't really care about. But you can see all of these fields are private fields. So there is no way for me to directly access the message field as such because it's private. So there is a function, there's a method exposed that's called intrainer. So I'm going to use that to get the message. And once I have gotten the message, I'm going to say let transaction equals to, I'm just going to construct it into my own type. So from is basically transaction dot from, to is basically transaction dot to, amount is transaction dot amount, which is the correct. And then this timestamp, I'm going to use the one that I get from there just to ensure that these two things are same, because there might be a certain delay between that timestamp and the timestamp when I calculate it right now. And if they are different, then the hash will be different and the sign won't be verified properly. So that's why I'm just going to use the timestamp from this, the one that I'm receiving. Everything looks fine. I have my transaction object now. So I'm going to say let mute chain equals to self dot blockchain. And I'm going to put a mutex lock on this so that further when I'm like, I'm going to modify the chain now by adding a transaction. So I am putting a lock here so that only I can modify it, like this thread can modify it, not anyone else. Then I'm going to say let success equals to chain dot add transaction, and then the transaction that I just created above. Don't necessarily need to clone it because I'm not going to use it anywhere downstairs. So yeah. So far I created a mutex lock and I added my transaction to the chain and I got a success result that could either be true or false based on the success of me adding the transaction to the chain. And finally, I'll create the return type, that is again this response and everything. Just a reminder, it comes from tonic, not something that we have defined by ourselves. Success is this value. And the last thing is message. So we can close this for now. Yeah. So message is based on the success. So if the transaction is successful, then it's added to the pool, or let's just say transaction accepted. And if it is not, then we can say transaction failed. So that is our first function, the submit transaction function. The next is get balance. This is a really simple function. Get balance, just query the chain and get the balance. Then this will return something like above. So let's copy this for simplicity. Put it here. So for get balance, the return type is not transaction response, rather it is balance response. And this is also pretty similar. So let's copy it. It takes an instance to self, and the request is not this, but balance request. Where am I getting these things? The balance request, balance response, and everything. I'm just getting this from here. the protobuf file. So balance request is already there. Balance response is also already there. Transaction response, as you can see, it's already there. And I'm just type aliasing this as proto transaction because this is also transaction here. And my local type transaction is also called transaction. Just to avoid confusion, I'm calling it proto transaction. And proto transaction comes from here. So you can see transaction as proto transaction. I'm importing it as that. Right. Now try this function, let address equals to request dot into inner because we need the message, the inner message. That's why. And then finally we need the address. And chain equals to self dot blockchain dot log dot await. Same as before because we need a mutex lock and let balance equals to chain dot get balance. This get balance is the method that we just defined above for our blockchain implementation, and it takes an address. So I got the balance now, and I'll just construct the response. And this is it. So you can see the return types are satisfied. It expects response type in the OK. So that's what I gave him. And this balance is the balance that I'm fetching from the chain. There is one last method. That's the last and the last thing in the project itself. It's the request faucet method. It's going to be a little long, but bear with me. So as usual, let's just copy this. It's easier that way. And then put it here. And let's call this request faucet. Before diving into this, do you have any doubts?
What is this? I have a more general question later on.
Sorry, come again.
I'll have another question, but once you finish it.
Okay, sure. So this is going to be of type faucet request, and this is going to be of type faucet response. Again, faucet request and faucet response is something we're getting from the proto file, request and response. And status is something we have from Tonic itself. We're importing that from Tonic itself. All right. Where did that go? Yep. So let address again equals to request dot into inner dot address, because we need the address because this is the address to which we are gonna send the coins after the faucet transaction. And then we will create a transaction like we did here. So let's just copy and paste this. So from address is going to be faucet address. To address is going to be the address that we just received, or the address that we just got from the message. And we want to clone it. And amount is something that we can define by ourselves. So let's just hard code it. Let's say it's 1400 coins, any arbitrary amount. And timestamp, we're gonna use the same thing as this. Yeah. Signature is going to be empty because it's for a transaction. Yeah. This start to string. We also constructed a transaction here, the faucet transaction. Now let's add it to the chain, to the transaction pool. Let's chain equals to this. You can copy and paste this. You can copy and paste this whole thing starting from there. Yeah. And then we're going to mine a block with the transaction. Faucet transactions are mined immediately, at least in our chain. So we're going to create another SCP object like we did earlier. Then create a new key pair. Let's call it faucet key. So ideally, this should actually come from your ENB files because this should not change. But every time you request for faucet transaction, this kind of changes. Struct block chain dot mine pending transactions. We use the faucet key that we just created. If it is successful, then add a log that the faucet transaction was successful and it was mined successfully. Created faucet block with hash. Only I could type. Let's block dot hash. Then send a response. So this is covered for the success part. But what if this fails? What if we're not able to mine the transaction? What if we're not able to get a block? So for that, we're just gonna create an error response. Let's just copy this thing. There is no faucet amount in our case, so let's just hard code 1400. This works. Yeah. Amount is 0 because it's already failed. So let's success is false, amount is 0. Message is ready to process faucet request. That's it. So we are essentially done with the chain. Let me just check if I think we had a missing implementation somewhere. Difficulty is what did they undo? Well, probably missed something somewhere. Yeah, we missed these things. And the start method, obviously, those things we may have missed. So let's implement them quickly. implemented for consensus. And okay, the start method. So how do we start it? We're going to spawn a new thread because one thread is responsible, the main thread is responsible for running the gRPC server, is responsible for mining. So we spawn a thread. It's getting annoying, yeah. And then async move. Again, it's all syntax for asynchronous coding in Rust. And SCCP equals to CCP 256 K1 new, I mean SCCP object. Then I'm going to generate a key. It's going to be public key equals to the net key pair. Let's write this. Then I'm gonna log the minus address. Mining encode public key dot serialize. Yeah. Something else came with this. I don't need this. Next, we're gonna loop because it's a continuous process checking for transactions in the transaction pool. We keep on checking, and if you find transactions, then you mine them. So the loop, let's create a scope. Let's let new chain equals to acquire a mutex lock. And if chain.transaction pool has a set number of transactions, only then start mining. So for testing purposes, we can set the limit to 1, as in if there is one single transaction in the transaction pool, then immediately. Yeah. And then once you mine a block, sleep for some time, 5 seconds, for example. Cool. We are done now. So just to go over this method again, it spawns a thread, it creates a new miner key, and it starts mining, it starts listening to the transaction pool in a loop. And when the number of transactions in the pool is greater than 1, or you can say if it is at least 1, then the miner drains all the transactions from the pool and starts mining them. If you want it to be strictly greater than 1, then you can just remove the equal to and it will work. Yeah, this part is unimplemented. Remember now. It just needs some logging. Transaction verification failed. This also needs some logging. Insufficient balance confirmation. Correct. So yeah, our blockchain code is now ready. Anyone has any doubts?
That's from me.
You had a question somewhere else, right?
Yeah, but it's like a more generic question. So you implemented a blockchain system for sending money, and I was wondering, okay, why do we need another one? Why do we need a platform to implement these um, another way to send money if we have already a number of these blockchains for sending money? So would a company just implement one and then use it for, I don't know, their clients? That's
Sending
the
money.
idea. Let's say a bank will open a one for themselves. What was the idea behind it?
Yeah, so blockchains are not exactly used only for sending and receiving money. There are a lot of other implications also, like real world asset exchange and everything. Just
Okay.
to name a few. But why should you create a new blockchain? You should create a new blockchain if you are creating something unique. This is just a general skeletal explanation of how a blockchain functions in general. This is not actually a production ready unique blockchain that people are going to use tomorrow, like you said.
Right, yeah.
Yeah, this was just created to explain people how the internals of a blockchain work, how the components of a blockchain can be coded using Rust. Of course, it has room for a lot of improvement, but this is like kind of like stripping down a fully functional blockchain that is out there in production to its grassroots level.
Okay, I'll ask it a different way. Okay. I totally understand why would someone learn how to write a web application, okay? Because you need web applications for millions of companies, okay?
Okay.
But I don't understand, but I don't think that thousands of companies will want to have their own blockchain.
Yeah,
I mean,
companies don't usually have their own blockchains
sorry?
because companies don't usually have their own blockchains.
Exactly. So
Yeah.
so you have very few blockchains in the world at the end, right? And we
No, no,
won't.
no. You do have a lot of blockchains in the world, but
How many? I mean, hundreds, thousands, or how many do you think there are?
uh, could be hundreds, could be thousands. I'm not really sure, but it's a
Okay,
big number. It's not
okay,
like
no, no,
very few
that's
number.
fine, that's fine. But it's not like millions. So the question
No,
is, okay, so I see lots of ads, for example, for people writing code. Okay, so programmers who know blockchain, whatever level. What kind of work do they do? I mean, they don't implement new blockchains, right?
no, they build blockchains from scratch. Like I am a core protocol engineer, so basically that's what I do. That's my job, building blockchains from scratch. And
Okay.
we implement basically different protocols that are not pre-existing, or we implement protocols that are suited to our needs. That
There are some,
we implement basically custom blockchains. So if you
okay.
have a business need, you implement a blockchain based on that particular need, which no other public blockchain offers you.
Right. Okay. But yeah. So, but what we are saying here is that that it's not like in the millions. It's like the thousands, the number of these blockchains.
Yeah, it generally depends on a use case. So if you already have a blockchain that so kind of caters to some use case, then you don't really need to create a new blockchain that does the same thing.
Okay. But do people keep improving blockchain? So what is a
Definitely.
besides what you do? Okay. So that's fine. There are a few people like you who build blockchains from scratch, right? But there are lots of jobs out there. It seems to be that one of the most popular job titles in for us developers or the areas of development is somewhere in blockchain. So what do all these developers do?
It's not only building blockchains from scratch, like there are a plethora of job roles available. One of the most popular ones is a smart contract developer. So basically, you build smart contracts and deploy them to already existing blockchain platforms. So like
Okay.
Ethereum uses Solidity smart contracts. Our Polkadot can use, let's say, Ink smart contracts, for example.
Hmm.
Solana uses Anchor contracts. So that is, I think, by far the most popular role if you talk about jobs, smart contract development.
Okay.
And then there's a DApp developer like who builds mobile and web applications on top of existing blockchains and use them as the backend.
Mhm.
So it's not always only building blockchains from scratch, but also building
Yeah.
on top of blockchains that do exist.
Okay.
But you can think of it as a different discipline of blockchains, jobs of blockchains.
Right. Okay. Okay.
Okay, so I think we are done with the implementation. Let's try to run and see if it works.
Okay.
I do hope it works. This is the command to run it. Let's cross our fingers. Yep, it works.
Wow.
Okay, so now we have blockchain running on this address on this port.
Mhm.
Again, it's hard coded, so it should not be hard coded. It should be fetching it from some ENV or something, but it's hard coded. So let's just move on with that. And I will share my wallet screen now. Yeah, I hope you can see my screen.
Yes, I can see your editor right now.
Let's open the wallet screen now.
Another one.
So this is my wallet code that I wrote. It basically is a client that connects with the blockchain.
Okay.
Yeah. So there are various files here. So the command file basically defines the available commands. Like new command creates a new wallet. List command lists down the wallets that are available already. Balance command fetches the balance from the blockchain for that particular address. And send command sends transactions. And the faucet command requests money from the faucet. And then I have an errors file where I have defined a custom error called wallet error. So these are the various errors that are defined as an enum. And then I have also implemented the corresponding string representation by using implementing the display trait for them for this particular enum. And then I have added some conversions because I want to return only wallet error. So even if it is an IO error, I am converting it to some form of wallet error so that I can just return wallet error. I don't need to cater to different types of errors. And then at the end, I have a custom result type that returns a generic T when it's all right. But if it is an error, then it returns wallet error always. So this is the reason why I needed to do all of this, because these are potentially the errors that I will run into in my code. And if I do, then how do I convert them into wallet error? So I have written I implemented the from traits for all these particular errors. So if it is certification error, then it's this imparts error for the wallet error. If it is tonic transport error, then it is wallet error, connection failed error, and so on and so forth. And in the main file, I have basically implemented the command. So like what happens if a command is create wallet, then what should happen? If a command is list wallet, then what should happen? So on and so forth. In the models, I have defined some types. One of the types is key pair, that is a private key and public key pair. And the other type is wallets, that is basically a hash map of a wallet name mapped to a key pair. In the proto file, it's again the more blockchain that we had defined earlier in our blockchain also. It just includes the protocol into our code and creates a module out of it. Storage.rs, this load function, it checks the memory, and if the wallet file already exists, then it loads it into memory. And the save function basically writes to the wallet file. The add wallet function adds a new wallet to the already existing wallet file. So wallet file looks something like this. It's JSON basically. So I've already created two wallets for you and me. And the get wallet function gets a wallet by the name from its collection. And the resolve address basically takes a name or key. And if the name matches with the wallet's name, then it returns it. If the public key matches with the sum of, any of these public keys, then it returns the public key. Doesn't matter what name it is. And finally, if it is not a wallet that we have saved on us, even by name or by the public key. But if it is any generic, general valid public key, then also you can return it. It's valid. If it is neither, then you return none. And finally, this wallet is the gRPC implementation, the client implementation. This calls the functions. So there are some async functions like this get balance, which calls the RPC get balance from the on the blockchain that sits on the blockchain. So yeah, that is the entirety of the wallet application. So let's run this. So actually, this is also available as a crate on crates.io. So I have it installed. The package is called Merkle. So I'm not gonna run the code, but I'm gonna use the Merkle command.
Okay.
So let's create a new wallet. Just to show how to create wallets. New. Then let's give some name. Let's say code maven. And it says a new wallet code maven has been created. And if we check the wallets file, we can see there's a code maven already there with a corresponding public key and private key. So now let's try to send some money. First, let's check a balance. Merkle BLNCE for, let's check it for Gabor. As expected, you have 0 coins because it's a new wallet. We have not yet transacted or you have not received anything on the faucet. Yeah. So let's request some money from the faucet. And this works. Yeah. So you received 1400 coins in your wallet. And if we go back to the blockchain implementation, we can see that some blocks are added. So adding transactions from faucet to pool, it's added. 1400 transactions, 1400 coins are added. And then the faucet block is also created with the hash this. So like whatever you do here, the blockchain gets it because there are gRPC connections.
Okay.
So now let's try to send money.
Show me the balance. Show me my balance.
Definitely. You have earned it.
Okay.
We have 2800 coins.
Yeah,
Because
okay.
I called the faucet twice.
Yeah, good.
Now let's try to transfer some money. So send, is it, let's see, in the board, sort of, I'm going to take most of your money.
Well, you were hard, so it's okay.
Okay, fine, I'll take that 500. And yeah. So you can see I entered the name Sourav, but it said invalid because there is no address called Sourav. And you can
Okay.
see the address called Sourav, it's Sourav Mishra. So you have to
Okay.
enter the name. And you can see a transaction has been sent successfully. And
Okay.
if you look here, you can see it added the transaction to the pool.
Yeah.
So if you add one more transaction, let's say do the same thing, but with less coins now, the transaction is again sent successfully, and this is added, and
Mhm.
a new block is mined.
Yeah.
So that is the whole implementation of our blockchain and the client.
Wow. Okay.
So there are like a lot of areas to improve on, but this is like I could strip it down to the least complexity, and I came up with this.
Very nice. Very
And
nice.
I had removed some more features, then it might have become a really boring blockchain. So I tried to include all aspects of the blockchain while keeping it simple. So this is what I could come up with. It took longer than expected to explain it and write it down, but I hope at least it was worth it.
Yeah, yeah, I learned a lot. I still need to, I still need to go over this again and again, I guess, until it sinks in. But yeah, thank you very much. It
Yeah,
was excellent.
mm, you can follow the README. There are some areas where you can contribute. So if you like this project, then you can contribute
Yeah.
this to this project. So towards the end, there are some API enhancements that can be done. There are some consensus mechanisms that can be added, like we have not added for proof of stake or proof of authority, something like that.
Hmm.
And
And
there are,
do you, The changes you made here in this branch, are they all available on the main branch, or did you push this out, or
It's all available in the main branch. So I try to make it same as the main branch. So people who are following live can also be benefited, while people who are not following live and checking it out from the GitHub, they can also be benefited. The code
okay,
is same.
excellent. Well, thank you very much.
Anyone have a doubt?
I,
I expected something.
I'm overwhelmed, so so thank you very much for this presentation, and thank you everyone who stayed. And well, there were not many questions at the beginning. There were a few, and I hope that people who watched this video enjoyed it. And please like the video and follow the channel. And below the video, you'll find links to the repository as well, and to Sourav, so you can contact him if you want to, I don't know, work with him or just ask him questions. And I think that's it, right? Anything else?
I sent my Telegram ID on chat. So Radek, if you're interested, you can contact me on Telegram and we can chat if you want to talk about this project.
Excellent. So I can, whatever you like, I can share on this web page, or I can link to your, I don't know, I'm going to link to your LinkedIn page, and whatever you like. Okay?
Yeah, that works. Thank you so much.
Yeah, thank you very much. Okay, so thanks everyone, and see you next time. Bye bye.
Bye bye.